Good morning, fellas. We're going to start off today's video with going through some of the answers from the SciPad pages I set last week. So we'll just go through a couple of these. Let's start off with CH4. This is our Lewis diagram. We've got 4 regions of electron density. All of the regions are bonding. We've got no unbonding regions, meaning our shape is tetrahedral with a bond angle of 109, and our 3D shape will look like this. Remember, this wedge that's filled in means it's coming towards us. This dotted line going away from us means it's going away from us. Let's go down to NH3 here. This has got 1, 2, 3, 4 regions of electron density. 3 of them are bonded, 1's non-bonded, meaning our shape is trigonal pyramid or pyramidal. Its bond angle is 109 because it has the 4 regions of electron density, meaning its electrons are in a tetrahedral arrangement because this electron's pointing upwards. We've still got a tetrahedral arrangement, but our shape is trigonal pyramid because only the bonding regions determine the shape. Let's go down to SF2. It's got 1, 2, 3, 4 regions, which again is 109 degrees because it's tetrahedral arrangement, but it's only got 2 bonding regions, meaning our shape's bent like water, and we can draw it bent like this. Let's go down here. COCl2, we've got 1, 2, 3 regions of electron density. Remember, the double bond only counts as 1 region, meaning our bond angle is 120 degrees, and we can just draw the shape like this. It's completely flat, so we can just draw the shape like this. It's trigonal planar. Linear molecules we can just draw like this, since they're not actually 3D, they're just flat again. So tetrahedral, we draw like this. Trigonal planar, we can just draw flat, since it is just 2D, since it's a flat molecule. And trigonal pyramids we can draw like this without lone electrons on the top. See how lone electrons are on the top there? And importantly, we don't need to draw our... Let's have a look at this one. We've got lone electrons around the sulfur here on our Lewis structure. We don't need to draw them in our shape. Our shape is just what atoms there are, but we still draw electrons around the central atom because they determine the shape. Okay? If you didn't manage to do this one, that's okay. SO2 is a little bit tricky because the reason why it's tricky is this oxygen is only having 1 bond, which doesn't make sense because in all other cases oxygen has 2 bonds, which is why I don't think this molecule should be in level 2. It should really be in level 3, since you can draw it as having 2 bonds, but then you've got 5 bonds coming out of the sulfur, and that doesn't make sense either. So I don't like this molecule. I don't think it should be in level 2. But it is bent in either case. Okay, so today we're just going to have a really quick look at electronegativity. Okay? Electronegativity is a very key part of chemistry, and it determines how molecules interact with each other. So let's get started. Key principle. Some atoms want electrons and others don't. I put want in brackets because atoms don't want anything, they're little bits of matter, but they become stable when they get electrons, meaning they want them. So fluorine is 1 electron away from filling its outer shell of electrons to become stable. This is fluorine here. It's got 2 electrons on its inner shell and 7 on its outer valence shell. If it could just get 1 more, it would become stable. So it really wants that extra electron, or it becomes stable when it gets that extra electron. So it's the most electronegative element. Okay? Sodium only has 1 electron in its outer shell. This is its outer shell, it's only got 1 electron. Meaning, it doesn't really need more electrons, it's trying to get rid of this one to get the noble gas configuration. Which is why sodium plus, the cation for sodium, is why it's so common, because it gets rid of this extra electron. So it's one of the least electronegative elements. It really doesn't want the electrons. Here is our electronegativity scale. It's rated from 0 to 4 in terms of how badly the atoms want the electrons. You see fluorine has got the top rank. It's 4.0 because it really wants the electron to fill its outer shell. Same with chlorine. Chlorine's 1 electron away from filling its outer shell, and oxygen's 2 electrons away from filling its outer shell. So these elements here are really fond of electrons because it helps them to become stable. That's the key point. Notice that noble gases have no values because they've already got a full shell of electrons. They don't bond, meaning they have no values. And over here, the atoms are trying to get rid of their electrons to become stable, meaning they have a low electronegativity value. Okay? Sweet. When atoms form a bond, the most electronegative atom pulls the electrons towards it. So if we have a look at this bond here, it's between hydrogen and fluorine. If we go back here, we can see that hydrogen is less electronegative than fluorine. So what's happening is fluorine's saying, your electron will be mine, and hydrogen's trying to hold on to its electron, saying, no, it's my electron, don't take it. So they're sharing a bond. There's 2 electrons in this bond. Remember, they form a covalent bond, so they can each fill their outer shell. But the electrons are hanging slightly closer to fluorine because it's more electronegative. Importantly, this creates a slight negative region around one atom and a slight positive region around the other. How we draw this. We've got hydrogen here bonding to fluorine. Fluorine is more electronegative. It's pulling these electrons in the bond towards itself, and it's getting a slight negative charge. We draw this symbol here. This is, in chemistry we call this delta negative, which means slightly negative. Okay? This is slightly positive. If you could write these notes into your books, including this picture down here, you don't need to draw this lovely comic, but just this picture down here, that will be fantastic. So pause the video, write down those notes, and we'll end soon-ish. So those are the notes again, same ones as the previous page. To recap, covalent bonding is the sharing of electrons between atoms. This type of bonding occurs between 2 atoms of the same element, or elements close to each other on the periodic table. They share electrons so each atom can obtain a full outer shell of electrons. So this is a carbon-carbon single bond, and these are sharing these 2 electrons here, and it's also got 3 more. Carbon forms 4 bonds. In this case we've got 1 bond going to carbon, and there'll be 3 more bonds coming off this. I might end after this slide. If the difference in electronegativities between bonding atoms is 2.0 or more, it's an ionic bond, which means we'd have an ionic solid. So let's have a look at this. Atom A has got a weak pull of these electrons. Atom B has got a very strong pull. So this could be fluorine, this could be sodium, okay, or this could be chlorine and this could be sodium to make sodium chloride. There's a really big electronegativity difference between these elements. So what happens, instead of sharing these electrons, the electrons are just being transferred. It's an ionic bond. Okay? So we need an electronegativity difference below 2 for it to be a covalent bond and them sharing them. Okay? We'll get to more of this tomorrow, but for now, thanks guys for watching this video.